The Humanoid 100, Mapping the Humanoid Robot Value Chain. The physical embodiment of AI touches a $60 trillion TAM, global GDP, and the meaning of work. Morgan Stanley presents the Humanoid 100, a global mapping of equities across a range of sectors and regions that may have an important role in bringing robots from the lab to your living room. As Gen AI continues to migrate from the digital world, bits, bytes, to the physical world, atoms or photons, investors are beginning to grasp the enormity of the potential disruption while struggling with paths to expression on the theme. In our original Humanoid Blue paper, we introduced the Humanoid 66, a list of both enablers and beneficiaries that we believed were most exposed at the time. Since then, commercial developments evolved at a rapid pace, especially in China, with many new players announcing their involvement or intentions to become involved. Investor interest seemed to accelerate meaningfully following NVIDIA CEO Jensen Huang's 2025 CES presentation, where he devoted roughly 40 minutes to the topic of physical AI and robotics. We are now fielding questions daily from a broad scope of global investors on how to play the embodied AI theme across a number of angles. Morgan Stanley has worked across dozens of sector teams to help our clients map differing stock expressions that are exposed to one of the most rapidly developing verticals of embodied AI. We do not pretend to present the Humanoid 100 as an exhaustive list, but rather a starting point in a conversation that will last many years and is sure to follow some exciting and unpredictable chapters along the way. We invite our clients to challenge our list and offer their own ideas of what should or should not be included as they become ever smarter on the humanoid theme and its adjacencies. Exhibit 1, Time Series of Company Transcripts Mentioning Humanoid. Exhibit 2, Time Series of News and Media Reports Mentioning Humanoid. Introducing the Humanoid 100 Stock List, our mapping of the humanoid value chain. The Humanoid 100 is the product of collaboration across Morgan Stanley's global equity research team to create a list of public companies exposed to the humanoid robot theme. Based on feedback from investors over the past 6 to 9 months, we focused more on the first derivative enablers that we believe will be consequential in building, training, and integrating a humanoid robot ecosystem. We compiled the list through a mix of discussions with our global team of analysts and conversations with subject matter experts on critical technologies and key players, supplemented by our own proprietary research to find the most exposed names globally. We then divided the companies into brain, semis, software, body, industrial components, and integrators, developing full humanoids. For every company included in the Humanoid 100, we include details on size, stock liquidity, core business competencies, rationale for inclusion, and current humanoid involvement if applicable. Currently, 52% of companies are reported to be currently involved in humanoids, and the remaining 48% are either close competitors of companies known to be involved or ones that our analysts believe have material potential to eventually be involved. For a copy of the underlying Humanoid 100 database or our US-Chinese humanoid TAM models, please reach out to your Morgan Stanley representative. Note, this is a constantly evolving space with an expansive list of hundreds of global companies involved or with reasonable potential to be involved in humanoids. There is a large subset of companies we chose to exclude due to either small size, limited current potential involvement, or lack of materiality. However, we expect there to be continued debate on which names and sub-industries may be better positioned on this theme over time. We look forward to a spirited debate and welcome all feedback. Exhibit 3, Introducing the Humanoid 100, Morgan Stanley's list of global humanoid enablers. One of our goals with the Humanoid 100 is to give investors an accurate view of the current composition of the humanoid value chain. Investors will notice that 73% of the companies confirmed to be involved in humanoids and 77% of integrators are based out of Asia, 56% per 45% out of China, respectively. A common refrain we hear from investors is the lack of Western firms to add to their humanoid portfolio outside of Tesla and NVIDIA. In our view, this is important information in and of itself as it represents the reality of the current humanoid ecosystem, which we expect may need to change materially over time. See the West's current experience with EVs, which has significant supply chain overlap with humanoids. Our research suggests China continues to show the most impressive progress in humanoid robotics, where startups are benefiting from established supply chains, local adoption opportunities, and strong degrees of national government support. Exhibit 4. 52% of companies in the Humanoid 100 have been reported to be involved in the humanoid value chain. The remaining 48% have not been reported, but we believe there is material potential for these companies to eventually be involved, if they are not already. Dissecting the humanoid anatomy. To make sense of the list and properly construct a portfolio, we believe investors need at least a cursory understanding of the makeup of the humanoid brain and body. The brain is composed of a mix of semiconductors and software, the most relevant being the foundational Gen AI models for autonomy and simulation models, digital twins for training. The body is primarily composed of sensors, cameras, lidar, force, torque, magnetic, etc., actuators, composed of motors, encoders, bearings, screws, and reducers, a web of wires and connectors, and a lithium-ion battery generally mounted in the center of the chest. The exterior is generally composed of a mix of aluminum alloys and plastics to minimize weight. For more technical details of any particular humanoid part, common engineering architectures, and the current technical barriers to manufacturing humanoids, see the Anatomy of a Humanoid section from our China industrial analyst, Sheng Zhong. Exhibit 5, Flow Diagram of a Humanoid Robot, Understanding the Interconnections between Various Components and the General Role. In the remainder of this report, we outline the contents of the Humanoid 100, review the humanoid investment case, dissect the anatomy of a humanoid, outline the latest on humanoid development progress, and review our humanoid TAM models. Humanoid 100 covering analysts. Exhibit 7, Humanoid 100 by Morgan Stanley covering analyst. To discuss a specific company on the list, please reach out to your Morgan Stanley representative or the relevant analyst below. Mapping the value chain Humanoid 100. The Humanoid 100 is Morgan Stanley's list of public companies currently involved in or otherwise materially exposed to the humanoid market. We compiled the list through a mix of discussions with our global team of analysts, conversations with clients on their preferred names to play, and our own proprietary research to find names that are involved in the value chain. We then divided the names into brain, semis, software, body, industrial components, and integrators, developing full humanoids. For every name in the Humanoid 100, we include details on size, liquidity, core business competences, rationale for inclusion, and current humanoid involvement if applicable. Currently, 52% of companies are reported to be currently involved in humanoids already, and the remaining 48% are either close competitors of companies known to be involved or ones that our analysts believe have material potential to eventually be involved. For a copy of the underlying Humanoid 100 database, please reach out to your Morgan Stanley representative. Exhibit 8, Introducing the Humanoid 100, Morgan Stanley's list of global humanoid enablers. Exhibit 9, Flow Diagram of a Humanoid Robot, Understanding the Interconnections between Various Components and Humanoid Brain, 22 companies. Companies in the brain category supply either the semis or the software AI models necessary to enable humanoid autonomy, including both training and inference. Foundational models. These are companies building the Gen AI models critical to enabling robotic autonomy. Through extensive training on vast sets of real and simulated robotic data, these models allow humanoids to understand natural language, learn from and imitate human action, and perceive their dynamic environments. The most well-known is NVIDIA's Project GR00T. Companies in the Humanoid 100, Alphabet GOOGL, Baidu, Meta, Microsoft MSFT, NVIDIA NVDA. Data Science and Analytics. These are companies developing software that allow robotics developers and users to capture and analyze the extensive amounts of sensor data captured at the edge. Companies in the Humanoid 100, Oracle ORCL, Palantir, PLTR. Simulation and Vision Software. Simulation is critical to training robotic models, allowing robots to learn their environments and use cases prior to deployment. These companies develop a range of digital twin or vision data capture technology used in robotic humanoid training. Companies in the Humanoid 100, Alphabet GOOGL, Dassault Systems, DSYFR, Hexagon, Hexa.bse, Meta, NVIDIA NVDA, Siemens, SIEDE. Vision and Compute Semis. These are the companies producing semiconductors that are the core of the robot brain, allowing robots to learn from, perceive, and/or interact with their environments. Vision-focused semis lie at the edge and allow robots to visualize their environments. Compute-focused semis exist either at the edge for real-time AI processing or at a data center to train foundational models or build simulations. Companies in the Humanoid 100, Ambarella, AMBA, Horizon Robotics, 9660HK, Intel INTC, Mobileye, MBLY, NVIDIA NVDA, Qualcomm QCOM. Memory. These companies produce memory, DRAM, NAND, etc., necessary in all computing, likely to become more relevant in robotics with further AI penetration. Companies in Humanoid 100, Micron, MU, SK Hynix, 000660KR, Samsung Electronics, 005930KR. Semi-designers. These are silicon design firms that could benefit from a wave of new humanoid-specific semiconductor development. Companies in the Humanoid 100, ARM Holdings, ARM, Cadence Design Systems, CDNS, Synopsys, SNPS. Semi-fabrication. The actual manufacturers of semiconductors, the largest of which is TSMC. Companies in the Humanoid 100, Intel INTC, Samsung Electronics, 005930KR, TSMC, TSM. Exhibit 10, Dissecting the Humanoid Brain. Exhibit 11, Humanoid Brain Companies. Exhibit 12, Rationale for Inclusion and Current Humanoid Involvement of Brain Companies. Humanoid Body, 64 companies. Companies in the body category supply components enabling humanoid locomotion, electrical distribution, sensing, or structure. Actuator parts. Actuators are mechanical devices that convert electrical energy into motion, either linear or rotary. The greater the degrees of freedom, DUF, required, the more actuators are needed. Humanoids currently in development are generally capable of between 16 and 60 DUF. Optimus Gen 2, in particular, uses 50 DUF, driven by 28 actuators, 14 linear, 14 rotary. The latest Optimus hand, likely for Gen 3, features 22 DUF versus 27 DUF in the human hand. Future humanoids will likely have greater and greater DUF over time. Humanoid companies will often design their own proprietary actuators tailored to the specific robot, but will source various components from a web of global suppliers, similar to how automotive companies often design the vehicle architecture but outsource manufacturing to various auto suppliers. We outline the primary components below. Bearings. Bearings are key to reducing friction in a moving system while maintaining rotary precision. Humanoids use a variety of bearing types, including ball bearings, roller bearings, and needle bearings. Degree companies in the Humanoid 100, NSK, 6471JP, RBC Bearings, RBC, Regal Rexnord, RX, Skifler, SHA0DE, Timken, TKR. Screws. Screws are components that convert rotational motion from a motor to linear motion, and thus are a critical component in linear actuators. Currently, both ball and planetary roller screws are used for humanoids, but this is largely due to the limited supply and cost of planetary roller screws. Over time, planetary roller screws should represent the majority of screws used in humanoids. Degree companies in the Humanoid 100, Hungley, 601100CN, Highwin, 2049TW, NSK, 6471JP, SKF, SKF.BSE, Shanghai Beatty, 603009CN, THK, 6481JP. Gearing and reducers. Reducers, as the name implies, reduce motor speed using various gear wheels to improve torque output and precision. They are a critical component in rotary actuators. Current humanoid designs use either harmonic or planetary reducers. Degree companies in the Humanoid 100, Harmonic Drive System, 6324JP, Highwin, 2049TW, Hota, 1536TW, Leader Drive, 688017CN, Naptesco, 6268JP. Regal Rexnord, RX, Shuanghuan, 002472CN, Timken, TKR, Zhongda Leader, 002896CN. Motors and rare earth magnets. Electric motors convert electricity into mechanical energy and are used in all electric actuators. Most motors create motion using rare earth magnets that repel against electrified coils of wire, creating a rotational effect. Humanoids generally use either frameless torque motors, lower technical barriers, or coreless motors, greater technical barriers. Degree motor companies in Humanoid 100, Eston, 002747CN, Leadshine, 002979CN, Moons Electric, 603728CN, Nidec, 6594JP, Regal Rexnord, RX, Sensata, ST, Shenzhen Innovance, 300124CN, Jiawei, 003021CN. Zhongda Leader, 002896CN. Degree rare earth magnet companies in Humanoid 100, JL Mac, 6680HK, Liners Rare Earths, LYCAU, MP Materials, MPUS, Northern Rare Earth, 600111CN. Encoders. Encoders are sensory devices that are fitted on and monitor the speed and output of a motor, sending back a signal to control variables such as position, speed, and torque. Degree companies in the humanoid 100, Nidec, 6594JP, Novanta, NOVT, Sensata, ST. Sensors. Humanoids are outfitted with a wide array of sensors to allow humanoids to perceive their environment and collect necessary data. We outline the primary types below. Cameras and vision sensors, captures full images, cameras, or light properties to enable humanoid perception. Degree companies in the humanoid 100, Analog Devices, ADI, Hexagon, Hexa.bse, Intel INTC, Keyence, 6861JP, Onsemi, ON, RoboSense, 2498HK, Sony Group, Sony, T Connectivity, TEL, Teledyne Technologies, TDY, Will. Semiconductor, 603501CN. A radar and LiDAR, enables depth perception through radio waves, radar, or lasers, LiDAR, to detect objects and measure distances. Degree companies in the humanoid 100, Aptiv, APTV, Intel INTC, Magna, MGA, RobotSense, 2498HK, Teledyne Technologies, TDY, Valeo, FRFR. A magnetic, detects presence of a magnetic field. Generally in humanoid hands and allows the robot to sense if it is touching something. Degree companies in the humanoid 100, Allegro Microsystems, ALGM, Melexis, MeleBE. A force and torque. Force sensors allow the humanoid to detect and measure weight and pressure. Torque sensors allow humanoids to assess the torque applied to its actuators. Degree companies in the humanoid 100, Kelly Sensing, 603662CN, Novanta, NOVT, Sensata, ST, T Connectivity, TEL. Batteries. Humanoids generally use a battery pack made of cylindrical lithium-ion cells contained within the torso of the robot. Companies in the humanoid 100, CATL, 300750CN, EVE Energy, 300014CN, LG Energy Solution, 373220KR, Samsung SDI, 096770KR. Analog semis, work with sensors to help regulate temperature, speed, position, electrical distribution, etc. Many sensors are technically a type of analog semi. Companies in humanoid 100, Allegro Microsystems, ALGM, Infineon, IFXDE, Melexis, MeleBE, NXP, NXPI, Onsemi, ON, Renesas, 6723JP, ST Micro, STM, Texas Instruments, TXN, Will Semiconductor, 603501CN. Body, wiring, thermal, the structure of the robot and method of power distribution and cooling. Companies in humanoid 100, Amphenol, APH, Aptiv, APTV, Magna, MGA, T Connectivity, TEL, Shushing, 603305CN, Sanhua, 002050CN, Tuopu, 601689CN. Diversified automation companies. These are companies that provide a wide range of automation robotics-related solutions such that they were best left in their own category. Potential to supply most necessary components given scale and expertise if there is sufficient demand. Companies in humanoid 100, Hun High Precision, Foxconn, 2317TW, Honeywell, HON, Rockwell Automation, ROK, Siemens, SIEDE. Exhibit 13, Dissecting the Humanoid Body. Exhibit 14, Humanoid Body Companies. Exhibit 15, Rationale for Inclusion and Current Humanoid Involvement of Body Companies. Humanoid Integrators, 22 companies. Integrators are companies currently building full humanoid robots or that have the reasonable potential to do so given their expertise in manufacturing other robotics or automation platforms. Most of these companies are larger, mature corporates that also have in-house robotics businesses. We note the vast majority of younger humanoid startups are currently private. We group the integrators below. Autos. There are a number of automotive companies currently developing humanoids, likely due to the engineering and manufacturing overlap combined with potential in-house use cases to reduce labor intensity and improve margins over time. Companies in humanoid 100, BYD, 002594CN, GAC Group, 2238HK, Hyundai Boston Dynamics, 005380KR, Tesla TSLA, Toyota, 7203JP, Speng, XPEV. Consumer electronics. Similar to automotive companies, these firms likely manufacture, or may manufacture, robots due to their expertise in scale manufacturing and ability to develop electronic architectures for robots using in-house talent. A number of these companies may see humanoids as an extension of household electronics and leverage humanoids as another method to penetrate the home. Companies in Humanoid 100, Apple AAPL, Hun High Precision Foxconn, 2317, TW, LG Electronics, 066570.HK, Samsung Electronics, 005930KR, Sony Group, Sony, Xiaomi, 1810HK. E-commerce and Internet. These companies would likely benefit from overlap between humanoid design and their existing technical expertise, and additionally could have in-house use cases to reduce costs over time. The companies in Humanoid 100, Alibaba BABA, Amazon AMZN, Naver, 035420, KR, Tencent, 700HK. Legacy robotics companies. These are legacy cobot manufacturers that have existed for decades but have the potential to eventually develop humanoids if they are not already doing so. The companies in Humanoid 100, ABB, ABBNCH, Midea Ikuka, 000333CN, Teradyne, TER. Humanoid near pure plays. These are young humanoid developers that are the closest to humanoid pure plays out of any company on this list. Exhibit 16, Humanoid Integrators. Exhibit 17, Rationale for Inclusion and Current Humanoid Involvement of Integrators. Humanoid 100 Composition. Exhibit 18, 52% of companies in the Humanoid 100 have already been reported to be involved in the humanoid value chain. The remaining 48% have not been reported, but we believe there is material potential for these companies to eventually be involved, if they are not already. Exhibit 19, Humanoid 100 Brain-Body Integrator Composition by Region. Exhibit 20, Humanoid 100 Regional Composition by Major Category. Thematics AI Mapping Survey. Our Thematics team conducted a survey in June 2024 incorporating results from Morgan Stanley Global Research Analysts to map out both the type and degree of AI exposure for all covered names. In the process of putting together our Humanoid 100, we cross-referenced with the AI mapping survey results. We'd note that more than half, 58%, of our Humanoid 100 are reported as either enablers in some form, either an enabler or enabler adopter. For materiality, the vast majority, 65%, of our list has at least moderate exposure, with 25% classified as at least significant, and 19% as core to thesis. Exhibit 21, Analysts surveyed AI exposure of companies in the Humanoid 100. Exhibit 22, Analysts surveyed AI materiality of companies in the Humanoid 100. Exhibit 23, Analysts surveyed pricing power of companies in the Humanoid 100. Exhibit 24, PE rank of Humanoid 100, cons. Exhibit 25, PE versus consensus 3 years revenue CAGR, full. Exhibit 26, PE versus consensus 3 years revenue CAGR, excluding outliers. Exhibit 27, LTM performance of Humanoid 100 versus the S&P 500. Exhibit 28, LTM performance of brain companies in the Humanoid 100 versus the S&P 500. Exhibit 29, LTM performance of body companies in the Humanoid 100 versus the S&P 500. Exhibit 30, LTM performance of integrator companies in the Humanoid 100 versus the S&P 500. Exhibit 31, LTM performance of US and Canadian companies in the Humanoid 100 versus the S&P 500. Exhibit 32, LTM performance of China and Taiwanese companies. Exhibit 33, LTM performance of other APAC companies in the Humanoid 100 versus the Nikkei 225 and Kospi Composite. Exhibit 34, LTM performance of EMEA companies in the Humanoid 100 versus the DAX Composite and FTSE 100. The Humanoid Investment Case. The below is an excerpt from our Humanoids Blue Paper. 4 years, machine learning was limited to self-reinforcing software algorithms. The advancement of large language models, LLMs, and Gen AI have made a great leap into the field of robotics, accelerating how physical machines learn, through natural language, imitation, and simulation. Gen AI is transforming how robots learn by giving them a chance to observe and imitate behaviors in both the physical and virtual world, connected through natural language and iterated in the data center. Similar to how large language models, LLM, help drive ever greater capability of ChatGPT, multimodal models, MMM, are driving innovation in robotics. AI algorithms can significantly shorten the R&D cycle by automating repetitive tasks, enhancing data analysis and predictive capabilities, enabling virtual simulation, and optimizing design and testing processes. As an AI-adjacent field, humanoid hardware development can now directly benefit from the increased capital formation and R&D investment into the robotics theme. AI leaps into the physical or atomic world. AI is all around us. AI listens to you. AI sees your face and body. AI knows where you are right now. AI can read. AI can write. AI can talk. AI can make a picture of cats wearing little cowboy hats playing canasta. But other than running loads of algos and activating a few switches, AI rarely ever actually moves. In nature, motility is an organism's ability to move independently under its own energy. According to fossil records, the earliest evidence of motility on Earth traces back to bacterial flagella, spindle-like extensions used for locomotion, in the Precambrian era. The lines between mobile device and robot are beginning to blur. Exhibit 35, Top Humanoids from Pop Culture. Why humanoids? Many investors reading this report will ask the question, why do we need robots shaped like humans? There are indeed strong arguments for robotics to take many highly specialized forms: robot arms, snake-shaped robots, robot dogs, robotic dust, and as many form factors as you can imagine. However, many robot and AI experts say the strongest argument for robots in a human form factor is that in a world already created for humans, the environment is already brownfield for humanoids. NVIDIA CEO Jensen Huang recently stated, "The easiest robot to adapt into the world are humanoid robots because we built the world for us. We also have the most amount of data to train these robots than other types of robots because we have the same physique." Additionally, think of the great variety of tasks that humans are able to perform with our bare hands or using tools and the multitude of machines designed for human hands and fingers. Exhibit 36, Pros and Cons of Humanoids versus Specialized Robotics. Framing the TAM. As of November 2023, the U.S. labor force stands at around 162 million people. At an average salary of $59,428, the U.S. labor market is worth just shy of $10 trillion annually. According to Statista, there are approximately 3.4 billion people employed worldwide. Assuming a $9,000 per worker annual salary implies approximately a $30 trillion global labor market, roughly 30% of global GDP. Given the thousands of individual jobs performed by humans, the TAM exercise required a far more detailed analysis across job stratification to understand the path of humanoid substitution gated by economic paybacks, supporting supply chain infrastructure, and other factors. As such, we built a proprietary Morgan Stanley humanoid TAM model to address a more realistically available subset within the theoretical $30 trillion universe over time. In our US TAM model, we forecast a humanoid population, cumulative installed base, of 8 million units by 2040, $357 billion wage impact, and 63 million units by 2050, $3 trillion wage impact. While our analysis does not currently consider a humanoid installed base greater than the existing human labor pool, there are scenarios where the economic benefits of the technology could make this a reality. At his most recent AGM, Tesla CEO Elon Musk expressed his belief that humanoids will eventually outnumber humans by 2 to 1 or more. I think the ratio of humanoid robots to humans will probably be at least 2 to 1, something like that. 1 to 1 for sure. So, which means like somewhere on the order of 10 billion humanoid robots. Maybe 20 billion or 30 billion. Exhibit 37, Cumulative Number of U.S. Jobs with Humanoid Optionality, 2028 to 50, MN. Exhibit 38, Cumulative U.S. Wage Impact, 2028 to 50, $BN. 1 billion humanoid robots by the 2040s? Tesla CEO Elon Musk has been increasingly focused on Optimus, Palo Alto Engineering Center, in recent months, per his comments. Tesla first unveiled its humanoid robot, Optimus, on September 30, 2022. The bipedal robot included 28 actuators in 2 categories. 1. Rotary actuators, consisting of harmonic reducers, ball bearings and sensors, for rotating motion such as shoulders and elbows. 2. Linear actuators, comprising planetary rollers, ball bearings and sensors for linear motions like human muscles. 12 actuators for 2 hands. Many more details have been kept internally at the company. In January of this year, Elon Musk said he expected to see over 1 billion humanoid robots in operation by the 2040s. At Tesla's June 13, 2024 annual shareholder meeting, Mr. Musk stated he expects to have at least 1,000 Optimus robots working at Tesla next year, and that things are gonna scale up very rapidly from there. In the same meeting, Mr. Musk expressed his confidence that humanoid robots will eventually outnumber human beings and probably be 20 billion or more, no timeline shared. A dynamic, fast-changing competitive landscape. Beyond Tesla, dozens of startups and established firms have engaged in humanoid robotics development on the back of the rapid growth of Gen AI in 2022-2023. We note even before NVIDIA's keynote speech in March 2024, which left little to the imagination about the company's intentions for physical AI, robotics were a recurring AI theme, including at the Morgan Stanley TMT conference last March. After a number of false starts, an array of venture investors and companies across are betting on the promise of embodied AI. Humanoid startups Figure AI and Agility Robotics were valued at $2.6 billion and $1.2 billion, respectively, in private funding rounds last year, with the broader theme attracting major investors including OpenAI, SoftBank, Tiger Global, Amazon, NVIDIA, and Microsoft among others. Additionally, major public companies, across industries ranging from automotive to consumer electronics, are actively involved in humanoid development, while others are actively partnered with humanoid startups to explore potential future use cases. Exhibit 39, Selection of Private Humanoid Companies Startups. Exhibit 40, Selection of public companies involved in humanoid development or exploring implementing humanoids in the workplace. Robotics having a ChatGPT moment. According to Vincent Van Hook, Senior Director for Robotics at Google DeepMind, experts in the robotics community refer to 2 years ago as the good old days, as he explains how LLMs and Gen AI have very abruptly flung the field of robotics from an isolated robot island firmly onto the AI flywheel. The science of LLM, large language models, and generative AI had long been seen as completely separate from the world of robotics, actuation. These worlds are colliding and the impacts are profound. We've been here before. In 1821, Michael Faraday ran an electric current through a wire suspended over a magnet in a glass, observing the rotation of the wire. This marked not only the discovery of how electrical energy can create mechanical movement, the first electric motor, but it also connected two areas of science that until then seemed unrelated, electricity and magnetism. Albert Einstein found connections between the properties of physical matter and light that were previously never conceived, E=mc². Might we be on the verge of unlocking the relationship between Gen AI and robotics? Exhibit 41, Seemingly unrelated areas of science can combine with profound effect. Exhibit 42, Public company documents and transcripts mentioning humanoid. Exhibit 43, News reports mentioning humanoid. Cybernetic collective robotic learning. Imagine for a moment a humanoid robot standing in front of a kitchen island on which an onion sits on a small plate next to a paring knife. Now imagine a large warehouse with 1,000 humanoid robots each standing next to a kitchen island with the onion on a plate next to a knife. As each trial and error accumulates among the group, the entire population learns at the collective rate of the best robot at any point in time. The aggregated learning of the cybernetic collective spools up, to achieve an accelerated frontier of group learning. When the physical practice is completed with a winning robot having peeled its onion better than the other 999, best practices can then be shared and further improved through hundreds of millions of trials among their digital twins in a simulated omniverse. Exhibit 44, with NVIDIA Project GR00T, humanoid robots train in a simulated version of reality called Omniverse. The below image shows digital. Have you seen or interacted with a robot today? Some of you may have. Most of you reading this at the beginning of 2025 likely have not. This rather nostalgic period of human technological history is quickly passing. The ongoing LLM Gen AI revolution is in the early days of crossing over into robotics. LLM and robotics were long seen as vastly different areas of science. But there may be far more overlap in how the advancement of LLM accelerates the training and learning of the robot, whether it is a car-shaped robot or a human-shaped one. The AI brain is searching for its robot body. Humanoid versus autonomous cars. Autonomous vehicles, AVS, are robots. Rather simple robots, in the form factor of a car. By simple, we mean there are only three primary actuation outputs of a robotaxi: 1. Steering wheel, 2. Accelerator pedal angle, and 3. Brake pedal. However, the operating domain is extremely complex, public roads riddled with unpredictable elements. We believe that the humanoid time to commercialization will materialize faster than AVS given the variability of the AV operating environment, real world, and corresponding safety implications, human passengers, pedestrians, versus the humanoid form factor, which can learn in a geofenced domain, warehouse, factory closed work cells. Even though humanoids have more physical outputs, the difficult operating domain, safety concerns, and regulatory scrutiny that autonomous vehicles face pushes their adoption curve out to the right in our view. Key drivers of humanoid adoption. The story of humanoid robotics involves an understanding of three primary domains: AI, robots, and people. At various stages, advancements in AI, multimodal models, neural net training, compute, may progress faster than the physical science of robotics, i.e., optics, actuation, battery, manufacturing, which may march along its own path of potentially nonlinear improvement. All the while, a number of drivers of labor factors across industries and regions will significantly determine economic payback periods, adoption rates, and social acceptance. Exhibit 45. Labor availability versus AI and robotics acceleration. While advanced humanoid development remains in its early stages, we believe the path of progress over the past few years in the adjacent areas of 1. Gen AI, 2. Actuators and mechanics, and 3. Battery storage are proving to be significant contributors to humanoid development. Further advancements in these three areas will be key to achieving humanoid commercialization. Exhibit 46. As contributing technologies have advanced over the past decade, intelligent humanoid development has continually increased in relevance. A number of gating factors must also be considered. Widespread commercialization of humanoid robots at scale must overcome a host of technological challenges as well as a wide range of societal, policy, safety impediments along the way. On the tech side, creating humanoids able to navigate the nuances and complexities of human environments will likely require continued advancements in Gen AI as well as efforts to tailor these advanced models specifically for humanoids. Additionally, further refinement of precision actuators, sensors, and battery capacity will be critical to improving the scope of tasks that can be executed by humanoids. Despite decades of modern robotics development, the sudden and rapid rise of Gen AI models may create scenarios where the mental capabilities of humanoids surpass the physical capabilities, opening the door to a range of potential hardware bottlenecks that will need to be addressed as humanoids become exponentially smarter. The social, policy, safety considerations as they relate to AVS helps us understand the range of potential hurdles for humanoids. However, we believe the ability to train humanoids using digital twins or in closed-off, geofenced work cells, as opposed to public streets, gives humanoids a relative advantage in approaching potential safety regulations. Exhibit 47. Potential hurdles to humanoid adoption. Leveraging the Morgan Stanley Asia Industrials Cortex, we assess the humanoid bill of materials, BOM, and map the key enablers within the humanoid supply chain. From China Industrials, Shenzhong, to Japan Industrials, Lisa Jiang, and China Auto Suppliers, Shelley Wang, we dive into the inner workings of a humanoid, breaking down component costs and the potential for future cost reduction. Per our estimates, building humanoid robots could range from $10,000 to $300,000 depending upon configuration and downstream application. For example, per primary component supplier price quotes and proprietary analyses, we estimate Tesla Optimus Gen 2's current BOM is $50,000 to $60,000 per unit, ex software. However, with the benefit of scale, the introduction of AI algorithms to significantly shorten the R&D cycle, and the utilization of cost-effective components from China, we see opportunities for significant cost reduction to achieve CEO Elon Musk's targeted Optimus selling price of $20K. Exhibit 48. We estimate current total X software BOM for Tesla Optimus at $50,000 to $60,000 per unit. Anatomy of a humanoid. The below is an excerpt from our Humanoids Blue Paper. What goes into a humanoid robot? Shenzhong China Industrials. As the embodiment of AI, humanoid robots are designed to think and act like humans. AI enables robotic brain function, underpinning the robot's intelligence level and the range of potential use cases. Mechanical parts enable the body function, underpin manipulation, and the BOM reduction potential. We believe future AI plus machinery improvement will decide the pace of humanoid adoption. The operating system, AI plus motion control system, is the most valuable part of a humanoid robot since it underpins the humanoid's intelligence level, including multimodal perception, logical thinking, and motion control. The AI chip, mostly provided by AI chip players such as NVIDIA, though we note Tesla reuses its autopilot algorithm for Optimus, perceives input information and generates instructions after logical thinking. The motion control system, which receives the instructions from the AI chip, controls the joints to perform commands sent from the AI chip with high precision and stability, and also, in return, provides real-time feedback to the AI chip. AI algorithms can empower the humanoid's operating system mainly by improving scalability, precision, and stability. In the long term, OEMs with the leading operating systems could drive both the direction of humanoid technological advancement and the pace of humanoid mass production. Currently, humanoid AI algorithms are still in the beginning stages of development, requiring lots of on-site validations, algorithm iterations, and hardware run-in for perfection. We believe AI algorithms can empower the humanoid operating system by improving its scalability. The humanoid operating system, integrated by humanoid OEMs, is usually specifically designed for a model or series in different scenarios. AI algorithms can improve versatility of the operating system, thus accelerating penetration of humanoid robots in different downstream applications. Precision. AI algorithms can effectively improve motion control precision with real-time monitoring capabilities, autonomous learning and task optimization, and unsupervised simulation and testing. Stability. Integrated with a variety of high-precision sensors, AI algorithms can improve the humanoid operating system stability with processing massive multidimensional sensor data, providing more granular data analysis, and indicating potential failures by early identification of anomalies. Humanoid actuators are core to performing human-like motions, acting as the robotic equivalent to human joints or muscles. Over time, humanoids will need greater amounts of actuators to facilitate greater degrees of freedom. Hardware plans can significantly vary across different humanoids in terms of degrees of freedom, DoF, hands design, sensor sensitivity, etc. We include an overview of notable humanoid hardware below. The bot brain, or central computer, is a system-on-chip, SoC, that processes the wide array of inputs and outputs used to drive all the hardware used on the robot, cameras, Wi-Fi module, audio, etc. For Tesla, the design for the bot brain is largely derived from Tesla FSD hardware and software. The humanoid body is mainly composed of actuators and supporting systems, battery pack, structural parts, thermal system, etc. Degree actuators are devices that enable motion in a system, both rotational or linear, similar to human joints. The greater the degrees of freedom required, the more actuators that are needed. Currently, humanoids in development generally are capable of between 16 and 60 DoF. Optimus Gen 2, in particular, uses 50 DoF, driven by 28 actuators, 14 linear, 14 rotary. The actuators themselves are comprised of a combination of screws, reducers, motors, sensors, ball bearings, and encoders. Degree structural parts are supporting material around the humanoid body, such as the skeleton and outer shell. The Optimus Gen 2 loses 10 kilograms without sacrificing its structure and performance, primarily from the use of lightweight materials such as PEEK, polyether ether keton, and high power density actuators. PEEK is a synthetic material often used as a metal substitute due to its excellent strength and light weight, which helps to reduce overall energy consumption while preserving performance. Exhibit 49, linear and rotary actuators are comprised of screws, reducers, motors, sensors, bearings, and encoders. Exhibit 50, overview of key parts used in a humanoid robot. Exhibit 51, humanoid motion can be driven by electric, hydraulic or pneumatic drive system, but electric-driven designs. Exhibit 52, hardware design of selected humanoid models. A worldwide supply chain. Shenzhen, China Industrials. Screws, motors, reducers, and sensors are the key components in machinery manufacturing. While the high-end component markets are dominated by Europe, US and Japan companies, Chinese companies are competitive in lower mid-range products where they aim to provide valuable products. However, there is still a large gap between the lower mid-range versus high-end products in terms of precision, stability, payload, and production process optimization capabilities. Screws are components that convert rotary motion and linear motion into one another. They are widely used in CNC machine tools, manufacturing equipment, robots, precision instruments, and other downstream applications. Humanoids, such as Tesla Optimus, mainly use ball screws and planetary roller screws for linear actuators to perform high-precision motions. However, these components have high barriers to entry and expensive production equipment and raw materials. Today, high-end screw manufacturing is dominated by Europe, Rolvis, SKF, etc., and Japanese companies, NSK, etc. There is also still a wide gap in efficiency, payload, and precision between high-end Western and Japanese producers and Chinese companies. However, some Chinese companies, Hongli, Best, etc., have started to penetrate the high-end market and have proceeded to demo validation for humanoid OEMs. Motors are used to generate driving torque and are mounted on the humanoid joints to control motion. On humanoids, frameless torque motors are widely used for both linear and rotary actuators to facilitate manipulation due to their small size, compact structure, light weight, small rotating inertia, and low starting voltage. Coreless motors are generally used in human-like hands, featuring higher energy saving, low voice, high useful life, and high torque. Frameless torque motors have a relatively low technology barrier. Germany's Kollmorgen, private, dominates in high-end frameless torque motor for high-end applications, while Chinese products are widely used for other low and mid-range applications. Kingco, not covered, is the leading Chinese supplier and one of few that can provide high-quality frameless torque motors. On the other hand, coreless motors have a much higher technology barrier, with concentrated applications in medical and military equipment, drones, etc. Currently, foreign suppliers account for greater than 85% market share in China. Chinese companies entered the market in the 2010s, but there is still a large performance gap between domestic and imported products on no-load speed and rated torque. However, we note that for coreless motors used on humanoid hands, Chinese companies such as Moons have already penetrated the humanoid supply chain and are running demo validation for OEMs. Reducers are used both for reducing motor speed and for improving the torque output and motion accuracy of humanoid joints. Planetary reducers, harmonic reducers, and RV reducers are the three primary categories of reducers. Different humanoid design require different type or quantity of reducers. All three of these primary reducer categories are dominated by Japanese companies, Harmonic Drive, Shimpo, subsidiary of Nidec, Naptesco, etc. Today, Chinese companies still have a large performance disadvantage on both precision and stability. However, we note that leading Chinese players, such as Leader Drive, have sent harmonic reducers for demo humanoids. Sensors, including vision sensors, force sensors, inertial sensors, temperature sensors, etc., are the essential hardware for humanoids' multimodal perception both internally, perception of its own position, and externally, perception of touch, vision, hearing, etc. Force sensors are more vital sensors for humanoids to achieve smooth and real-time force adjustments under various scenarios. 6-axis force sensors, the most complex force sensors, can measure payloads from any direction and bear payloads 5-20x higher than rated measurement ranges. ATI, a subsidiary of Novanta, NOVT not covered, is the inventor of the 6-axis force sensor and dominates the market, while most Chinese companies still lag without long-term accumulation in sensor calibration and decoupling. Other first movers such as Kunwei, private, and Sunrise Instruments, private, have begun to penetrate the sensor supply chain for humanoids. Assessing the humanoid bill of materials. There is a wide range of potential BOM costs for humanoids, largely depending on design complexity, material, and market positioning. Under our estimates, building humanoid robots could range from $10,000 to $300,000 given different configuration and downstream application requirements. For instance, China's Unitree announced its G1 humanoid would be priced at $16K with a simplified algorithm module, halved degrees of freedom, lack of linear actuators, shorter battery life, and lower carrying capacity. In contrast, with an estimated selling price at $250,000 in 2025, Agility Robotics' Digit is specifically designed for logistics, featuring a high power capacity and payload, high man-machine interaction intelligence, and a higher degree of balance or stability. Using Tesla's Optimus Gen 2 as an example, we estimate the current total X software BOM at $50,000 to $60,000 per unit, using price quotes from various component suppliers. However, we note this is using quoted prices for individual components used to create the robot. For a player building humanoids at scale, such as Tesla, the BOM could likely be significantly lower given various relationship, bundling, and/or bulk discounts with the various component suppliers. In our view, Tesla's Optimus has significant opportunity for cost reduction to achieve CEO Elon Musk's targeted selling price of $20K. We break down the BOM for Optimus Gen 2 by function. The bot brain is based on a Tesla SoC and additional outputs and inputs, e.g. Wi-Fi, camera, audio, etc. For the brain itself, we estimate the hardware cost is $2K a humanoid, 4% of total. Note, This excludes any potential software cost, e.g., FSD training costs. Our all-body motion is driven by 28 actuators, 14 linear actuators and 14 rotary actuators. The upper body, shoulder, elbow, arm, hands and waist, requires 16 actuators which we estimate could cost $26K humanoid, 47% of total, and lower body, pelvis, legs, feet, requires 12 actuators which cost $26K humanoid, 48% of total. Our other supporting systems including the battery and various structural parts cost $419 per humanoid, 0.8% of total. When breaking the components down by product type, the key 5 parts of sensors, screws, motors, reducers, bearings cost $20K, $11K, $11K, $7K, $434 per humanoid, accounting for 37%, 20%, 20%, 13%. 0.8% of the total BOM. Exhibit 53, we estimate current total X software BOM for Tesla Optimus at $50,000 to $60,000 per unit. Exhibit 54, Optimus Gen 2 BOM breakdown by parts. Exhibit 55, Optimus Gen 2 BOM breakdown by function. Tracking humanoid progress. Patent filings. Exhibit 56, monthly global patent application filings mentioning humanoid, latest data as of the 19th of November 2024. Exhibit 57, global patent filings mentioning humanoid by office over the past 5 years. Exhibit 58, top filers of U.S. patent applications mentioning humanoid over the past 5 years. Exhibit 59, public company documents and transcripts mentioning humanoid. Exhibit 60, news reports mentioning humanoid. Exhibit 61, notable humanoid unveils since 2022, blue equals USA, yellow equals China, green equals EMEA, red equals rest of Asia. Exhibit 62, humanoid unveils by year and country. Exhibit 63, humanoid unveils since 2022 by country. Exhibit 64, humanoid unveils since 2022 by primary use case. Exhibit 65, monthly China humanoid company funding activity. Overview of major humanoid robots. Exhibit 66, notable humanoids with specs, 1/2. Exhibit 67, notable humanoids with specs, 2/2. US and China humanoid TAM adoption estimates. Note, the underlying Excel file for the TAM model discussed in this section is available upon request. Please reach out to your Morgan Stanley sales representative to obtain the model. US humanoid TAM estimates. As part of our humanoid blue paper published last June, we conducted a bottom-up analysis on the US labor market to assess each occupation's humanoid ability and estimate the humanoid TAM, US only. We started by gathering all 831 U.S. civilian occupations using the Bureau of Labor Statistics May 2023 Occupational Employment and Wage Statistics Survey. Working with our economics team, we assigned one of 4 values to measure the humanoid optionality of each occupation as follows. A strong potential, 46% of occupations. Degree: these are jobs that are predominantly unskilled and most likely to be perceived as boring, dangerous, and/or repetitive. Extremely unlikely to be performed by an AI model due to physical requirements of the job. Degree: for the purposes of our TAM model, we assume 70% of employees in these positions are substitutable with humanoids, i.e., 70% optionality factor. A moderate potential, 9% of occupations. Degree: these are jobs that are often physical in nature or which require a physical presence but are not necessarily unskilled or obviously perceived as boring, dangerous, and/or repetitive. Degree: for the purposes of our TAM model, we assume 50% of employees in these positions are substitutable with humanoids, i.e., 50% optionality factor. Lower potential, 19% of occupations. Degree: these are jobs that require complex human-to-human interaction or specialized skills not likely to be easily replicated by a robot, X. Doctors, supervisors, engineers, etc. A notable amount of these jobs are also more likely to be performed by an AI model rather than humanoid robots due to limited physical requirements. Degree: for the purposes of our TAM model, we assume 30% of employees in these positions are substitutable with humanoids, i.e., 30% optionality factor. A limited potential VNA, 26% of occupations. Degree: these are jobs that require a significant amount of complex human-to-human interaction or could more feasibly be performed by an AI model rather than a humanoid robot due to limited physical requirements. Degree: for the purposes of our TAM model, we assume none of the employees in these positions are substitutable with humanoids, i.e., 0% optionality factor. Using the humanoid substitution risk framework, we multiplied the number of employees in each occupation by the relevant humanoid optionality factor and then by the median annual wage for the given occupation. Note, this analysis is an illustrative effort to depict how humanoids could potentially be adopted in certain industries and how the TAM could be captured over time. Our timeline analysis also does not account for the possibility that the introduction of humanoids could create new sectors, expand existing sectors, or create new job opportunities for humans. For simplicity, the analysis also assumes no growth in the total size of the US labor market and its existing industries. Based on our analysis, we believe 75% of occupations and 40% of employees in the US have some degree of humanoid ability. This amounts to an estimated addressable market of $3 trillion, or 63 million humanoid units in the US alone. While this estimate considers only the US, we note that a TAM based on the global labor market could be greater by multitudes of magnitude. Exhibit 68, Humanoid Substitution and US Wage Impact by Tier, 2030 to 50. Exhibit 69, Cumulative US Humanoid Adoption, 2028 to 50, Millions of Humanoids. Exhibit 70, Cumulative US Wage Impact, 2028 to 50, billion. Overlaying an average selling price per humanoid and a replacement rate assumption onto our units adoption analysis, we estimate the total revenue generated by the US humanoids market each year. We assume an initial average selling price per humanoid in 2028 of $150,000 each, which declines to $50,000 by 2040. Post-2040, we assume a modest price increase of 0 to 1% per year driven by inflation offset by further technological advancements. We also assume a replacement rate of 8 years per humanoid. Based on these assumptions, we estimate that the US humanoids market could generate $4 billion total revenue by 2030, $240 billion total revenue by 2040, and $1 trillion total revenue by 2050, with rapid acceleration in revenue growth occurring in 2040 to 50. Exhibit 71, US Humanoids Market, Total Revenue, $BNS. China Humanoid TAM Estimates. Shenzhong. We introduce our China Humanoid Market Forecast Model to assess the market potential in China, expecting the market to reach RMB 12 BN, RMB 216 BN, RMB 6 TR by 2030 E divided by 35 E divided by 40 E divided by 50 E, with volume to reach 1.5 MN, 7.4 MN. 59 MN by 2030 E divided by 35 E divided by 50 E, respectively. We factor in China's low cost of labor and massive population, estimating a lower adoptability compared to US similar industry. Also, we believe a significant price cut is critical for humanoid to become a mass market product. We anticipate the ASP and BOM to decrease at CAGR of 8% and 11%, respectively. While the incremental volume could bring meaningful growth, there is short-term margin pressure to upstream manufacturers in China. Exhibit 72, China Humanoid Market Size, RMBBN. Exhibit 73, China New Humanoid Adoption, K-Unit. Exhibit 74, China Humanoid ASP versus BOM. Valuation Methodology and Risks. Tesla Inc., TSLA.O. Our PT of $430 is comprised of 5 components. 1. $86 per share for core Tesla auto business on 5.2 mm units in 2030, 9% WACC, 14x 2030 exit EBITDA multiple, exit EBITDA margin of 16.1%. 2. Network services at $172, 65% attach rate at $200 ARPU by 2040. 3. Tesla Mobility at $90 on DCF with $7.5 MN cars at $1.46 mile by 2040. 4. Energy at $65 per share, and 5. Tesla as a third-party supplier at $17 per share. Risks to upside. Disclosure on service revs. Increased FSD attach rate. Cost milestones on new battery. New model intro, Cybertruck, Multivan, Semi. 3-road party battery win. Geographic penetration and new capacity. Risks to downside. Competition, legacy OEMs, Chinese players, big tech. Execution risk, multiple factory ramps. Market does not recognize Dojo-enabled services up, lower than expected attach rate and RPU. China risk. Dilution. Valuation.